For separation of a binary mixture of components 1 and 2, the adsorption selectivity of species 1 with respect to species 2 is defined as the ratio of the molar loadings of component 1 with respect to that of component 2 divided by the partial fugacities of component 1 with respect to that of component 2. We could use the partial pressures in place of the partial fugacities if the gas mixture is not at too high pressures. With increasing pore occupancy of the gas molecules within the pores, the adsorption selectivity may either increase, decrease, or undergo selectivity reversals. And today I would like to highlight these three scenarios. The background material to my presentation is available in my two papers listed here, both in ACS Omega 2020, 2021. Watch also my video presentations, packing effects in mixture separations, and the IAST for mixture adsorption equilibrium on my YouTube channel. We start by examining the unary isotherms for metaxylene and paraxylene in AFI zeolite. AFI zeolite consists of one-dimensional channels that has a corrugated structure, and the dimensions are 7.3 angstrom at this point here, and in this grooves it is 8.4 angstrom. The metaxylene and paraxylene molecules cannot stand upright within the channels because the heights are too long, and they reside within the 1A channels by assuming a reclining position. The experimental data for the unary isotherms are shown here. Blue triangles for metaxylene and red circles for paraxylene. Both components have a saturation capacity of 0.8 moles per kilogram. The binding constant is slightly larger for paraxylene than for metaxylene, and the continuous solid lines are fits of the unary isotherm data using the single-site Langmuir model. Irving Langmuir obtained the Nobel Prize in chemistry in 1932. The single-site Langmuir model is written as follows, where theta 1 is the partial occupancy of component 1, in this case metaxylene. The partial occupancy of component 2, paraxylene, is the molar loading of component 2 divided by the saturation capacity. Both the saturation capacities are equal to one another, and B1 and B2 are the binding constants for components 1 and 2. F1 and F2 are the partial fugacities of components 1 and 2. For a binary mixture of paraxylene component 1 and metaxylene component 2, the component loadings for mixture adsorption may be determined using the mixed gas Langmuir model that is written as follows, where theta 1 and theta 2 are the partial occupancies of components 1 and 2, paraxylene and metaxylene, and the partial occupancies are defined as the ratio of the component molar loadings to the saturation capacity, QSAT, and this is then calculable from the binding constants B1 and B2 for species 1 and 2, and the partial fugacities F1 and F2 for the two components. For the case in which the partial fugacities in the bulk gas mixture are equal to each other, the component loadings are plotted here. Red line is for paraxylene and the blue line is for metaxylene. Since the binding constant of paraxylene is higher than that of metaxylene, the component loading of paraxylene is higher than that of metaxylene. The adsorption selectivity of component 1 with respect to component 2, paraxylene to metaxylene, is defined as the ratio of the component loadings to the corresponding ratio of partial fugacities, and from this expression we derive that the adsorption selectivity is simply the ratio of the binding constants for components 1 and 2. And the adsorption selectivity is plotted here, and the value is about 2.6 and is constant over the complete range of total gas phase fugacities. So the adsorption selectivity is constant in this case because the saturation capacities are equal to one another, and the adsorption selectivity is simply the ratio of the binding constants. An important assumption made in the derivation of the binary Langmuir model is that the saturation capacities of components 1 and 2 are equal to each other. This requirement is difficult to meet in practice, as illustrated in this graph that shows the unary isotherms for a variety of gaseous molecules in MFI zeolite. MFI stands for mobile 5, and it has a intersecting channel structure with straight channels and zigzag channels. Linear molecules can align themselves easily along either the straight channels or the zigzag channels. We note that the hierarchy of saturation capacities is hydrogen, the highest, with a saturation capacity of about 30 molecules per unit cell. The next is carbon dioxide. Then we have methane, nitrogen, ethane, and propane. The longer the chain length, the lower the value of the saturation loading. Here's a snapshot showing the location of molecules of CO2 and CH4 within the intersecting channels of MFI zeolite. This graph here plots the adsorption selectivity for 5 different binary mixtures of propane and methane, carbon dioxide and hydrogen, carbon dioxide and nitrogen, methane and nitrogen, carbon dioxide and methane, and the adsorption selectivities are plotted as a function of the pore occupancy. For occupancies below about 0.3, the adsorption selectivities in all 5 cases are practically independent of pore occupancies. However, with increased pore occupancies, the adsorption selectivity may either increase, as is the case with CO2 methane, For CO2 nitrogen, the increase is only very slight. However, for propane, methane, and CO2 hydrogen, at high pore occupancies, typically larger than 0.6, there is a significant decrease in the adsorption selectivity with increased pore occupancies. The explanation is to be found in the differences in the saturation capacities of the constituents in these 5 mixtures. Let's first look at the methane nitrogen mixtures. The unary isotherm for methane is shown here in the green squares. The cyan colored stars are for nitrogen. The saturation capacities are practically the same, and the binding constant for methane is larger than that of nitrogen. That explains that the selectivity is in favor of nitrogen. The saturation capacities are practically identical, and therefore the adsorption selectivity is almost independent of pore occupancy. For CO2 methane, we note that the unary isotherms show a higher saturation capacity for CO2 than for methane, and with increasing pore occupancy, the selectivity is in favor of the component with the higher saturation capacity. This is because when the pores get increasingly filled up, the vacant spaces are more easily filled by the guest component that has the higher saturation capacity. This is an entropic effect, and further details are provided in my publication ACS Omega 2021. Look at CO2 nitrogen. The differences in the saturation capacities is in favor of CO2 that has a higher saturation capacity, and therefore the vacant spaces in the pore topology at high occupancies is more easily filled up with CO2 that has a higher saturation capacity. Now we look at propane and methane. The saturation capacity for propane is about 12 molecules per unit cell. For methane is about 18 molecules per unit cell. And at low pore occupancies, the selectivity is in favor of propane. However, with increased pore occupancies, the selectivity reduces from, say, a value about 150 to a value about 80, because with increased pore occupancies, the vacant spaces are more easily occupied by the smaller guest, which is methane in this case. The same is true for CO2 hydrogen mixtures. At pore occupancies below about 0.5, the adsorption selectivity is strongly in favor of CO2. The adsorption selectivity is about 100, but decreases to about 40 at high pore occupancies, because hydrogen, the smaller molecule, is able to occupy the vacant spaces in the pore landscape more easily than the slightly bulkier CO2. So whether the adsorption selectivity remains constant, increases or decreases, depends on the differences in the saturation capacities, and at increasing pore occupancies, the component that is more favored is the component with a higher saturation capacity because the vacant spaces are more easily filled up. The mixed gas Langmuir model is unable to provide a quantitative description of mixture adsorption in scenarios in which the gas constituents have large differences in saturation capacities. In general, it is necessary to use more rigorous models for mixture adsorption equilibrium, such as the ideal adsorbed solution theory of Myers and Prausnitz. Indeed, for the 5 mixtures that were considered in the foregoing slide, the molecular simulation data for adsorption selectivity for propane, methane, CO2 hydrogen, CO2 nitrogen, CH4 nitrogen, CO2 methane mixtures are quantitatively described with good accuracy by the IAST model that is shown here with the dashed lines. So if the unary isotherms for the gas species have large differences in saturation loadings, it is of vital importance to use the IAST and abandon the mixed gas Langmuir model to describe mixture adsorption equilibrium. We now move on to separation of mixtures of ethanol and 1-propanol in Chabazite zeolite that consists of cages separated by narrow 8-ring windows. Ethanol is the smaller guest, and it is possible to accommodate 4 molecules of ethanol within a single cage at post-saturation conditions. And this is the unary isotherms for ethanol, and you will see that the saturation capacity amounts to 4 molecules per cage. 1-propanol is a slightly larger molecule, and at saturation it is only possible to accommodate 2 molecules per cage. This is the unary isotherm for 1-propanol. 1-propanol, being the longer chain molecule, has the stronger binding constants. Indeed, the ratio of the binding constant for propanol, B2, to that of ethanol, B1, is about 200, whereas the saturation capacity is higher for ethanol by a factor 2. For adsorption of mixtures of ethanol and 1-propanol with partial fugacities that are equal to one another in the bulk fluid mixture, the adsorption selectivity of 1-propanol to ethanol were determined from the equilibrium data determined from configurational Bayes Monte Carlo simulations. The 1-propanol to ethanol adsorption selectivity is plotted here as function of the total occupancy of the gas molecules within the cage window structures of Chabazite zeolite. We note that at pore occupancies below about 0.5, the adsorption selectivity is about 10 in favor of 1-propanol. When the pore occupancies increases beyond a value of 0.5, the adsorption selectivity gets increasingly in favor of the smaller ethanol molecule that has a higher saturation capacity. and at a pore occupancy of about 0.65, the adsorption selectivity undergoes a selectivity reversal, and for higher pore occupancies, the mixture adsorption equilibrium is in favor of the smaller guest, which is ethanol. The dashed lines here are the calculations of the adsorption selectivity calculated using the IAST. The IAST is able to quantitatively capture the selectivity reversals in favor of ethanol at pore occupancies larger than about 0.7. For further background information on selectivity reversals, I refer you to my two publications listed here. Watch also my video presentation on packing effects in mixture separations and the IAST for mixture adsorption equilibrium on my YouTube channel.